Here are the audio notes for how to calculate pH for weak acids and bases. To begin with, recall in the discussion of strength in the last couple of class periods that a strong acid will completely dissociate in water, so its molarity is the same as the concentration of that hydronium ion, the H3O+. However, a weak acid does not completely dissociate. Quite frankly, usually it's to a very small extent. And because of that, we cannot assume that the molarity of, say, acetic acid is the same as its hydronium concentration. And remember, pH equals negative log of hydronium, so we need more math in order to solve this. When dealing with weak acids, one of the ways to identify that an acid is weak is it'll be given a Ka, an equilibrium constant for that acid. Bases have Kb values just the same, so if you see something with a K value, right there's an indication that it's weak. Recall that the smaller the value, the weaker it is. Hopefully recently you learned that of the halogenated acids, hydrofluoric acid is the weak one. It does not completely dissociate in water. Therefore, I have this equation shown here. If we wanted to solve for the Ka of that, we'd have to take the concentration of the products over reactants, which would be shown like this. The good news with this bit of equilibrium math that we're going to do is you are not going to see anything squared. It's always a 1-to-1 ratio, so it gets rid of a little bit of that math that was difficult to solve for in the past. Also recall when I do products over reactants, I am not including water because water is a pure liquid, so it does not have a concentration. So what we're going to do is we're going to solve a question right now. That question is going to be, what is the pH of a 0.25 molar hydrofluoric acid solution? To begin with, here's our dissociation equation. I'm getting rid of the water even, so I could have replaced this with just H+. Pretty common to see H+ instead of H3O+. Initial, I start with 0.25 molar and 0 of the other two parts. Oh, this is starting to look familiar. Change is next. Another nice thing about this equilibrium math that we're about to do, you will not have to solve for Q, the reaction quotient. We will always know the direction of the reaction because we're given a concentration of the acid. We want to figure out how much of it breaks down into these two parts. So here's my change, a minus x and a plus x for both of these, which means at equilibrium, I have 0.25 minus x, x, and x. K of HF, so the Ka of hydrofluoric acid, is a known value of 7.1 times 10 to the negative fourth. So if you know this value, you can now plug into that equation we did before. And I will show you on the whiteboard how to start to set this up then. Your K value, once again, 7.1 times 10 to the negative fourth, equals the concentration of the products, which are both x, so I'm going to call that x squared, divided by 0.25 minus x. Now, if I go back to my PowerPoint slides, what you'd want to do in an expression like this is you'd want to multiply both sides by 0.25 minus x, and then you want to get everything on one side of the equation and set it equal to 0. So again, I will go back to this slide and show you this is the expression that you would then get. Again, I always prefer to have my x squared as a positive value, so depending upon what side that you're adding things on, that might make a difference. If you recall from last unit, we then need to use the quadratic formula, where the number for the A value in this case is a 1, the B value is 7.1 times 10 to the negative fourth, and the C value is the negative value right here. Again, right here is your quadratic formula, negative b plus or minus square root of b squared minus 4ac all over 2a. Notice the plus and minus, so you have to do this equation twice. That's why I get two answers. Notice that one of my answers in this case is a negative value. And if I plug that in, I'd have a negative concentration of fluoride and hydronium ion. And you can't have a negative concentration, so 0.013 must be the correct answer. Now, I quickly went over that, and my gift to you is our textbook talks about an approximation where we don't have to do this quadratic formula stuff. I'm going to go back because I actually didn't even try to finish this question yet. Remember, I'm trying to solve for the pH. I'll get to that in a minute. I mentioned let's try the shortcut. Here's what the shortcut states. If you are given a value, like an expression like we have up on the board, 0.25 is the original molarity, 7.1 times 10 negative fourth, which if I wrote that out in long form would be 0.00071, is the K value. If there is more than a 100-time difference between the concentration and the K value, so in other words, these two values are not similar to one another power of 10 wise, what that should tell you is this minus x, this loss of a certain amount from the 0.25 is going to be a very tiny amount. So small that you might even say it's negligible. It's not going to actually change its value. I would use the analogy of it is similar to taking your mask before you get a haircut and after you get a haircut. In both of those instances, it's not really going to matter too much. So what we're going to do then is we are going to get rid of that part, that minus x part. So now if I were to simplify, I'd multiply both sides by 0.25. That gets me 1.775 times 10 to the negative fourth equals x squared. And if I take the square root of both sides from here, I get 0.0133, which 2 sig digs is 0.013, the exact same answer I had before. The reason why the AP test doesn't give you the quadratic formula is, for the most part, when you are dealing with weak acid base equilibrium, which is the most common type of equilibrium question you're going to see, is that this approximation will work, where you get rid of the minus x. Now, if you're someone who has the quadratic formula programmed into your calculator and you still want to use it, feel free to do so. Recall that you will have to simplify this original expression still in order to use that quadratic formula, so that might take a little bit of work. On the other hand, if you get rid of the minus x, because if it's a really weak acid compared to the concentration, it's not going to lose very much. So we're kind of approximating this. That approximation does hold true, usually. Again, the exception to when that approximation doesn't hold true is when the power of 10 between the K value and the original molarity are very similar. Now, if we do our last step, we still have to solve for the pH. So if I have my x value of 0.013, and I take the negative log of that, I get 1.89 for the pH. And this is where some of you might say, but wait a minute, why do I have 2 sig digs in 0.013, but I have 3 sig digs in the 1.89? So let's go back to this value again and go over that. Because really, my final answer was 0.013. Another way to write that would be 1.3 times 10 to the negative second. The power of 10 represents the number in front of the decimal. That's what's referred to as the characteristic, if you read that reading from when you're first introduced to pH calculations. These two digits then, the mantissa, represent how many digits should be past the decimal. That's why my answer had the 3 sig digs for this problem. As for the only other 2 points I have in this slide, bases are the exact same system. Weak bases act the same as it is with a weak acid. However, it's more common that you'll be doing weak acid work. I believe I will throw in a weak base problem here or there. Ka values, again, are known at specific temperatures because K is temperature specific. So in your book on page 671 is the Ka values, 679 are the Kb values. You don't have K values for strong acids or strong bases because they completely dissociate. So if you do products over reactants, it gives you kind of like infinity as a value. Two more topics to go over. The first one is percent ionization. For percent ionization, this is a calculation that's brought up in your book. You take the amount of acid ion that is in the ion form, that H+, and divide it by the original acid concentration. So in the question that we just did, 0.013 was the H+ concentration, 0.25 was the original molarity. That gives you 5.2%. Our textbook, when referencing that approximation, you don't have to write down this, by the way. Our textbook, when talking about that approximation, says when you are at a low percent ionization, that approximation does hold true. If, however, you are at a fairly high percent ionization, like above 10%, 20%, somewhere around there, you probably should be using the quadratic formula instead. One last thing to mention. Some polyprotic acids, which a polyprotic acid means it can donate more than one hydrogen, for example, H2SO4. Some polyprotic acids you could also do with these types of calculations. On the handout that you're about to work on, the very last question, question number 4, is an example of this. And what would happen is you have to take it part at a time, where each loss of a hydrogen has its own K value associated with it. So the first loss of hydrogen would have a K value versus the second one. Quickly explaining that before you have time to practice. Let's say you have the weak acid, hydrosulfuric acid. It does not donate both of its ions at the same time. It donates one acid ion at a time, which is why the first K value is 9.5 times 10 to the negative 8th. And then that HS minus so it might be called Ka2 versus Ka1, would have a value of 1 times 10 to the negative 19th. The second loss of hydrogen is always harder to lose than the first loss of hydrogen, but if you are to try to figure out what's the pH of a certain solution with that, you have to do the math that we did kind of twice. So first couple of problems in the worksheet you're about to work on are similar to what you just did with a weak acid for number 2. Number 3 is actually a weak base. Do the same sort of stuff, but remember negative log of hydroxide is the POH. And then number 4, that diprotic acid, more than one hydrogen can be lost, is a little bit trickier of a problem that I'd like you to be aware of, but quite frankly, our focus is usually going to be monoprotic acids. So that is the notes for weak acid calculations. We will be practicing it a whole bunch next class period as well, but let's give you a little bit of time to work.